So next up, we're going to talk about the atmosphere and ocean examples of convection. We're going to start with the ocean case because it's a little bit simpler. And we're going to look at a couple of examples of convection that are important in the ocean. So one of them is mixed layer convection. So remember last week we talked about mixed layers and how they were formed by the wind forcing at the ocean surface, mixing up the surface and creating this uniform density layer near the surface. It turns out mixed layers are also influenced by convection and by fluxes of heat and salt at the ocean surface. So we're going to look at that. And then we're also going to look at a process called deep convection, which gives rise to the bottom water that fills the world's oceans. So this is a crucial part of the global ocean overturning circulation, which is something that we'll come back to later in the course. So let's start with the mixed layer convection. So mixed layer convection is caused by a couple of mechanisms. One obvious one is if you cool the ocean surface, that will tend to cause a sinking plume, which will descend through the mixed layer. Another example, though, is if you strongly evaporate the ocean from the ocean surface, that makes the water saltier and therefore denser and also drives sinking. Now, it's a stratified environment because although the mixed layer might be well mixed up by the wind, at some depth you reach what we call the thermocline or the pycnocline, and then the density tends to increase quite rapidly with depth, or equivalently the buoyancy reduces with depth. Now, how effective the convection is at mixing up and deepening the mixed layer depends on how strong the buoyancy anomaly, how strong the air-sea flux is that is driving the cooling or the evaporation. So the stronger that is, the deeper the cold or dense fluid can reach beneath the original thermocline before it hits its neutral buoyancy level, and that sets the bottom of the region it can mix. So if you have this initial situation here with this mixed layer and stratification below, and we have an air-sea flux driving a descending plume, then after that convection has occurred, we're going to end up with this situation here with a significantly deepened mixed layer down to the neutral buoyancy depth of that plume. Now this happens in a cyclical fashion in the ocean. So there's a great example here from an ocean convection review, which is in your recommended reading. And here, this is the buoyancy flux over the time period from these ocean observations. And where it's blue, that's nighttime. So that's cooling that's occurring at night. And where it's red, that's heating that's occurring in the day. And what you can see is that each nighttime, where you get this strong cooling triggered, you get this deepening of the mixed layer. So here, nighttime, we get this deepening of the mixed layer due to convection. It re-stratifies during the day due to solar heating, and then you come to nighttime again, and you get this rapid deepening of the mixed layer. So this is a great example of mixed layer convection happening in the real ocean. Now, the same thing happens on a longer time scale, on a seasonal time scale. When you go into winter, you tend to get deeper mixed layers because you have cooler air that's cooling the surface and causing this convection and deepening of the mixed layer. And so there's an example of that here. If you get some observational estimates of what mixed layer depth is, so in December, January, February, which is Northern Hemisphere winter, you can see you get very deep mixed layers in the Northern Hemisphere oceans, particularly the North Atlantic. Whereas if you go to June, July, August, so Southern Hemisphere winter, you can see very deep mixed layers all through the Southern Ocean. So remember, the average mixed layer depth is around about 50 meters, so it's the blue color. But in these winter seasons, in the winter hemisphere, you get very deep mixed layers that could be many hundreds or even 1,000 meters deep.